All right, kiddos, let's try the second part of this problem and see what the final velocity of this mass is after 5 seconds. Okay, so the easy way to do this would be to find the area under the curve from 0 all the way to 5 seconds. All right, so the impulse is equal to 1/2 base times height. All right, so that impulse would be 62.5. All right, and then set that impulse, 62.5, equal to mass times the change in speed, or the change in velocity, sorry. So 62.5 equals the mass, and that initial velocity is 0 in this instance, so V final. Okay, and 62.5 divided by 5 leads to a V final of 12.5 meters per second. All right, there's a second way to do this, and you could actually find the area under the curve from 2 until 5, where you'd use the speed at 2 seconds as the initial velocity. And so this would be V initial equals 5 meters per second. And then you'd be solving for V final at 5 seconds. And the area under the curve would be the impulse. And I'll leave that as an exercise for you. All right. So earlier I did ask you to complete a problem that was in your More Practice with Momentum sheet, I believe that was called. Okay, and it was number 9, and it said an 85-gram bullet is shot at a 3-kilogram piece of wood at rest on the edge of a counter 1.2 meters high. If the bullet becomes embedded in the block and it lands 5 meters from the counter, what is the initial speed of the bullet? I love this problem. It's a really good IB level problem because it incorporates like all of the tools from the topic of mechanics. All right, so let's draw a picture. Okay, so I'm going to draw a counter. Okay, and here's a block of wood on the edge of the counter, and here's a bullet. Right, see, it's going that way. Sorry if you can hear my husband and daughter dancing downstairs. So here we want to know what the initial speed of the bullet is. And so I'm going to, let's write this as velocity of the bullet. And that's what we're looking for. Okay. As an aside, we know that the mass of the bullet is 85 grams. We want to make sure we convert that to kilograms. 0.085 kilograms. And then there's a piece of wood. So the mass of the wood is 3.0 kilograms. And then we've got a counter that's 1.2 meters high. And we know that when they come together, the bullet will embed in the block. And they will go flying together until they hit the ground. And this is 1.2 meters up from the ground. And this is a horizontal distance of 5 meters. Okay, we can call this y, like so. All right, So you can see that there's definitely a projectile problem happening here. And you can also see that there is a collision happening between the bullet and the wood, in which they stick together. Okay, so a totally inelastic collision. And we actually need to work backwards, because what we're trying to find is that how fast that bullet was going before it collided. Okay, so we should start with the projectile stuff. Okay, so we know that the mass of the block and the wood together is 3.085 kilograms. We know that this is, so let's go backwards here. So let's do a projectile problem, X and Y. So horizontally, we know that the horizontal distance is equal to that horizontal velocity times time. And the horizontal velocity is going to be this: how fast the wood and the bullet are traveling together after the bullet has collided with the wood. Okay. Vertically, we know V initial Y is going to be equal to 0. And then we can do we could do D equals 1/2 GT squared, right, as a result, to find out what the time is. And instead of D, we can write Y specifically, the vertical distance traveled. So let's go ahead and do that, solve for the time. So T equals 2 times the vertical distance traveled over G square root. And we end up with square root of 2 times 1.2 over 9.8, which is 0.49 seconds. Okay, and then we can go plug that in over here as well. Time is 0.49 seconds. Okay, now check this out. We know that the horizontal distance traveled is 5 meters. So if we take these two pieces and plug them into this equation, we can rewrite it as Vx equals horizontal distance over time, right? Which is 5 over 4.49, which is 10.2. Okay, so we know this is 10.2 meters per second. Okay, so now let's switch some colors here. We're going to go to red, and we need to do a momentum problem. Okay, so momentum initial equals momentum final, right? So the collision is happening right here. Okay, so right here when the block, or when the wood and the bullet collide together, that's going to be where our momentum final is happening. And over here when the bullet is moving, that's going to be momentum initial. Okay, so before the bullet collides with the wood, just the bullet has momentum. Okay, so we've got mass of the bullet times velocity initial of the bullet. After the collision, you've got the mass of the bullet and the mass of the wood together. They're stuck together, moving at a final velocity that we've called V sub x. Right up here, that's how fast those two are traveling together after the collision. Okay, and I'm going to go ahead and erase this initial subscript, because up here we've labeled that just as velocity of the bullet. Okay, so we know that this mass is 0.085 kilograms, and the velocity of the bullet is what we're looking for. The mass of the bullet and the wood together is 3.085 kilograms times 10.2 meters per second. And when we solve that problem, we end up with the velocity of the bullet when it was traveling by itself is equal to 370 meters per second. Pretty stinking fast, a little faster than the speed of sound in air, which isn't an unreasonable speed for a bullet. Okay, so that's one of our big old problems. Okay, one more big old problem, and then I'll set you loose. Let's take a look at this problem having to do with an object traveling and its mass is changing. Okay, a cart of mass M moves with a constant velocity on a frictionless road. Rain is falling vertically on the road and begins to fill the cart at a steady rate of W, which will be in kilograms per second. Find the velocity of the cart at time t seconds later. Okay, so we've got force times time equals mass times change in speed. Begins to fall at a steady rate of W kilograms per second. Okay, so we can say force equals W times change in velocity, and find the velocity of the cart after W seconds later. Okay, so the change in velocity would be equal to force over W. Okay, so we don't have any values to work with here, but I just wanted to show you a type of problem that can show up every once in a while, and it's a matter of unit analysis. W was written in kilograms per second, so if we divide both sides by time, this term right here, mass over time, is the abbreviation W, and you can use that to find the change in speed. Okay. All right. So on the Google Classroom, you'll find these videos, and you will also find a couple of resources that you can use for practice. Okay, so you can practice using graphs to solve momentum problems. Okay, there's some multiple choice conceptual review. And then there's what I've previously assigned as the momentum test review. We're not going to necessarily have a test, but I will assign you a quiz at some point that I would like you to complete and submit to check your work. Okay, so stay tuned for that. Also, if you want to reference the textbook, we talked about section 7.1 through 7.3, and there are some problems you can look at there just for practice. Please don't forget I'm available during class for questions and during flex for you guys from 10:10 to 11:10 on Friday. And if you have any individual questions that need to be addressed before that, please email me and I can set up a time for an individual video conference. All right, you guys, have a good week.